everyone, and welcome back to the Diaries of Space Explorers with me, your host, Gavin Tolometti. We're going to be speaking with Dr. Cecilia Leung, who is a planetary scientist specializing in the present-day water cycle on Mars and learning about how we can learn about Martian climate by studying Earth's climate. Cecilia got her bachelor's degree in physics and astronomy at York University and her master's and PhD in planetary sciences at the University of Arizona Lunar and Planetary Laboratory. Cecilia takes us on her space journey, where it all began by staring at the glow-in-the-dark stars in her bedroom, all the way to becoming a postdoctorate research fellow at the Jet Propulsion Laboratory in the United States. Without further ado, let's get right into the episode. So Cecilia, I just wanted to quickly formally welcome you onto the podcast. It's great to have you on.
Thank you very much for having me.
Yeah, so I wanted to go right back to the start for you on your journey. So what is it that brought you to space?
Yeah, I think for me as a kid, astronomy and the night sky was definitely my gateway into the space sciences. And so something about going camping and then seeing the night sky light up, and sometimes with a satellite that streaks across the sky, I think just being in that space inspires you to ask more existential questions like, what is our place in the universe? And so I have always loved going camping and watching the stars. And so for me, I actually grew up in the big cities. And so as you know, light pollution's a concern in the cities and obscures the sky. So what I actually did as a kid was there are those glow-in-the-dark stars that kids put on their bedroom walls. And for me, I'm a big nerd, so I took those glow-in-the-dark stars and put them on my ceiling in the formation of the constellations, so that I would actually be able to lie in bed and look up at my ceiling and see the stars where in their formation as if I was outside. So that interest carried me throughout my childhood. And I think when it came time for looking for a major for university, physics and astronomy really stuck out. And so I was looking for a program, a science program in Canada. That's where I grew up. And at the time, planetary science specific programs in Canada were few. There weren't that many of them. And so I actually chose to do my undergraduate at York University. And there I was enrolled in the physics and astronomy program, but it has a specialty in space sciences. It was more of an obscure program. I think there were only a handful of us in it. And it was a hybrid between the science-focused astrophysics courses as well as space engineering. And so I was taking classes, half my classes was all these engineers, and then half my classes was theoretical astrophysics. So I got to enjoy both, I guess. And I think I remember specifically that during my time at York, there were a couple of professors that were involved with the Phoenix Mars mission at the time. And I really gravitated towards that scientific investigations as well as instrumentations that were involved in planetary explorations. And so ever since then, I started looking into planetary sciences program, which brought me to my graduate studies in planetary sciences, and now my postdoc at the Jet Propulsion Lab.
Oh, wow. So you've really gone from quite a big jump, going from just looking at your glow-in-the-dark stars on your ceiling as a kid, and now you're working at the Jet Propulsion Laboratory. So,
well, we've all got to start somewhere, and for me, it was little plastic stars.
Well, it's because you mentioned those. As soon as you did, it reminded me when I was a kid and I had some on my wall, but I didn't go as far as you did and make the constellations. I just threw them up there, and I also had glow-in-the-dark planets that I put up. So that was as close as I managed to get. I think you took it one step further and made it even better. I feel.
it was definitely inspired by books that I seeked out from the library and just learning about astronomy in general.
Yeah, so it was definitely astronomy that got you interested, getting to look at all the different um, astronomical activity that happens up in the sky. And since you said you grew up in a big city, I'm guessing if you wanted to look up at the sky and observe all of this, you had to have driven quite far away from all the big lights to see everything.
Yeah, definitely. It was during camping trips that I was able to first encounter the night sky in that way. And I think even now, I think that public outreach for the younger generation is so important for looking at telescope nights and at the local observatory, because that's definitely a gateway that gets kids interested in the field.
And is that one of the things you wanted to take away from your love of astronomy was to get involved in outreach on top of getting to do all this planetary science research that you're doing now?
Yeah, it's all part of the job, and it's definitely outreach is definitely a part that I'm really passionate about. It's a dichotomy in my day-to-day life because with my research, when you're very deep into the sciences of it, it's mostly looking at a lot of computer codes, and sometimes I lose perspective of what drew me to that in the first place. And so when I'm speaking with younger children and families and just remind myself and be in their shoes and just see their eyes light up, it really complements and remind me of the interest that space exploration brings to humanity.
Yeah, it's always good to get a reminder. This is why I'm doing what I'm doing. I want to be able to talk about my work and see the interest and excitement in people's faces, even for something that can be quite complex. But once you explain it to them, they just like fall in love with it almost.
Yeah, definitely. And it's definitely a part of the skills that we need as scientists to be able to communicate our sciences in a way that the general public can understand and see how it's relevant to their day-to-day lives as well.
And I'm guessing in that case, you would say outreach definitely helped you develop those skills because it's not something that's usually taught at universities. It's something we usually have to pick up.
Yeah, communication skill is such an important skills that we have. And I think in terms of knowing your audience is so important. When we're researchers, we have to differentiate the type of presentations that we give to our colleagues at a scientific conference with our professional society versus one that you give to your local science center and try to connect with the public that way.
Yeah, no, I completely agree. I'm involved in outreach myself, or I try to be as much as I can than I used to ever since the pandemic started. So we've been very limited what we're able to do. But it's also part of the reason why I'm doing this podcast, because I want to be able to continue science communication, even from the confined comfort of my own room, instead of getting to go to observatories, museums, schools, and talk about space. So it's definitely something I miss. So so on your bio says that the research you do at JPL is to do with Mars. So why Mars? What is it that particular planet got your attention?
Yeah, so my current role at JPL is I'm a NASA postdoc fellow, and I'm working with the Mars Climate Standard team and looking primarily at the water cycle and vertical distribution of water in the Martian atmosphere. And what really got me is, first of all, as I was mentioning a little bit earlier, was that my involvement in my undergraduate led me to the professor's work with the Phoenix mission. And the Phoenix lander landed in the northern hemisphere of Mars, and that happens to be right near the polar ice cap. For Mars, it's one of those planets in our solar system that has a lot of similarities to Earth. And so by understanding the system on Mars and how it previously had much more water and how it transitioned to its current much more drier climate, we can potentially learn a little bit more about the evolution of planetary climate systems and apply some of what we know from other planets to what we know on Earth.
So you definitely think it could have applications to understanding climate change here on our planet, seeing how what our planet could be like if we're not taking care of it properly.
Yeah, for sure. For the Earth, this is the third planet away from the sun, and then so bracketing the Earth, we have Venus, which is much closer to the sun, and then we have Mars, which is the next planet out. And those three planets just evolved so differently in the age of the solar system. And for Venus, it's now this very hot planet. For Mars, it's very dry planet. And so trying to understand these three planets that had similar origins in terms of materials that formed them, and trying to understand what became of their climate systems now, really has applications on how we understand our climate on Earth and how it could evolve in the future, depending on what directions that we nudge the system.
Yeah, I think it's like a very incredible way to get involved and to really understand why you want to study the Martian climate in general, because you can see the potential that studying the climate on one planet can help us probably understand our own planet and maybe prepare for a worst case scenario if we literally do nothing to help it. And get your first involvement during your undergrad, you got to slowly see this, and then you eventually realize this is actually what I want to do. I want to learn more about this. I want to get involved. Let's get to JPL.
In a nutshell, yes, but it's it's not quite as simple as this is what I want to learn, this is how I got there. I think for myself, I'm a first generation college student, and so for me there was a transition period between my undergrad courses and then transitioning to graduate school and learning how to be an independent researcher. And because my family of origin wasn't able to guide me through that process, I really had to seek out mentors and sponsors that were able to teach me how to read and write scientific manuscripts, how to formulate a hypothesis and determine when this project is ready for when a conclusion has presented itself. Some of those things to navigate academia is something that doesn't come naturally, and I really appreciate having those mentors that were able to guide me along the way.
So how did you find these mentors, since it was it like, did you have to ask around during your undergrad, or did you get to meet them at conferences, or was it more of a usual interesting story?
There are many ways that one can find mentors, and it's typically not a direct "will you be my mentor?"
It never is. It never is.
Yeah, and it most of the times those relationships really come naturally and organically. You can tell when your work and somebody else's work has a lot of complementary elements, and then if they take interest in you and what you do, as well as try to promote your work to others and try to bring you onto their teams and really want to help you along as you're a scientist and further your career, it is somebody that you should really value your relationship and really appreciate their mentorship.
Yeah, and it sounds like you got the mentorship that you needed, because you were able to get to grad school, you were able to get a master's and a PhD at the same institution as well. You got both your degrees at the Lunar and Planetary Laboratory at the University of Arizona.
I would also like to say it was that easy, but
Oh, I
there are
would.
definitely
Yeah, I didn't want to imply that it was like, oh yeah, you just did this, checked it all off and went. I
oh,
imagine there was definitely some things to overcome and to develop and learn on the way.
I just meant in terms of the mentor process. It wasn't the first person that we met. It took some time to seek out individuals that were really willing and available to play those roles. But for myself, I did receive both my master's and a PhD from the same institution because at the Lunar and Planetary Science, at the Lunar and Planetary Lab at the University of Arizona, you are admitted into a PhD program and you receive a master's en route. This was when I first began my program, and there have been some changes along the way. And so I think now you can choose to, I think there's a route to just do a master's and not pursue the PhD if you don't want to do that. Mm-hmm. And everybody would choose differently depending on what their career ambitions leads them.
And for you, you wanted to get that PhD. That was definitely something you wanted to aim for.
I was lucky to be able to finish my PhD for sure, but I was also aiming to do that myself. What really motivated me to do so was because I really enjoy mission work, and to be a PI on a mission or even a research grant, it's much more advantageous to have your doctorate and be able to submit proposals as the principal investigator. And I knew I wanted to be involved in missions through a couple of activities during my grad study. I think one of the things that really instilled my love for mission was during the planetary science summer school at the Jet Propulsion Lab during my graduate years. And this is open to grad students as well as postdocs, both scientists and engineers. And the point of this planetary science summer school is this multi-week mission concept incubation exercise where you're working with a team, and as well as Team X at the Jet Propulsion Lab, to come up with a mission concept based on a New Frontiers budget. And so you really come up with a mission that from start to finish, and you have to meet all the requirements as a real mission would, including it needs to fall into below your cost cap. It has to meet thermal requirements, power requirements. You need to lay out all of your primary science objectives and be able to come up with a mission design that will meet these requirements. And so after going through that, as well as just in general, just really knowing I really enjoy mission, that's what motivated me to pursue the doctorate route and going right now to do my postdoc at JPL.
Yeah, and it sounds like going to that school where they actually put you in a scenario where it's like, this is sort of what a mission is going to feel like for you guys, where it comes to the planning, making sure you know exactly what needs to be checked before you even start the mission. You need to look at all the requirements, engineering-wise and science-wise. I think it's just as scary, as intimidating that must sound, it must have been an incredible experience, because it also maybe confirmed this is what you really wanted to do, because you were put in that situation where you realized, oh wait, yeah, mission work is something I want to do. That's what I want to strive for through my research.
Definitely. And part of what makes that experience really nice is that you are working with scientists and engineers, and both of those elements really need to come together and integrate before we have a successful mission. For myself, I came primarily from a scientist background, so I have these lofty ideas of what kind of sciences I want to do. I want to go explore ice volcanoes. I want to explore canyons, but when you have to apply engineering constraints to those, then you have to understand, well, we have to be able to safely land a mission. And so if you want to land inside a canyon, you have to understand what the wind conditions is like, what are your power conditions is like inside a canyon, so that you can still support your mission objectives, but within the realms and bounds of what is engineering and technologically feasible.
No, definitely. I think it's a lot of things that you have to consider, and there's a lot of things a lot of people don't realize that you need to consider when planning all these missions. It's usually why they take so long, because you have so many things you need to think about and then check if it's actually feasible. Can we actually do this before we could even, let's say, publicly announce saying we're going to send a lander to this planet, before someone goes, nah, I don't think so. And so, but I wanted to ask though, when you got to go to that school, you got all this experience. What is it that you had to prepare yourself for beforehand? Because I imagine since it was a new experience, you weren't entirely sure what was going to happen. How did you prepare yourself for it? In case if someone's listening right now and they're thinking about wanting to get more involved in planetary missions, is there something that you did that they could probably take away from it?
Yeah, I think part of it is to understand the importance of teamwork, as well as keeping a very open mind and keeping letting your imagination run to those places that pushing the envelopes of what we know. I think part of what make mission work and space exploration so interesting is that we are pushing the envelope of what humanity knows. We want to go to the edge of the solar system to learn, to go to planets that we've never been before, to learn more about them. And so it's important to keep your mind open, because sometimes when you go there, you don't know what you're going to discover. And so it's really cool that on one hand, it's really cool. And on the other hand, again, when I was telling you about how there are going to be constraints that needs to be met in terms of a team environment, it's really important to be to have those skills to be able to advocate for your science case, but also understand that this is a team effort, and then there could be drawbacks and pros and cons in terms of what type of instruments you bring. When we're sending these large missions to these faraway places, you have a lot of lofty goals and you want it to be a successful mission. And because there's something called, you have to also determine how much power you have to power the spacecraft with a number of instruments. And so you have to share some of the time, actually. Like sometimes you can have multiple instruments measure the observation at the same time, but sometimes you need to coordinate with different teams in terms of, well, we have this science I want to do, and so what kind of instruments and at what cadence I need. And so I think being able to work with others and make those coordinations and be just inspiring the team to work together is really important to have a successful mission.
No, I definitely agree. I think the teamwork is definitely an important one. I can't imagine a planetary mission succeeding if everyone's either yelling at each other and nothing happens, or everyone's constantly trying to, I guess, outsmart or outdo each other without anything productive being completed. So it's definitely something that you have to learn, not even just during that experience, but something you need to build up and learn as you go. And I'm sure everyone, and including yourself, has probably had to learn this, sometimes the easy way and then sometimes the hard way. And so after that school, when you now got your postdoctoral position at JPL, what was it about this particular research that really got you interested? I know before we talked about you got to you get to learn about the climate systems on Mars to understand what happened in its past and why it like what it is now, and how we could maybe apply it to Earth. Is there anything else, or is that the main reason why this really attracted you to this research?
I think there are a lot of different elements in terms of the skills that you learn in graduate school that applies to your postdoc and beyond. For some people, study one topic and you can go very deep into that topic, and others use the tools and models that they've built throughout their grad school and apply it to different places in the solar system or on Earth. And so I think part of me trying to understand the lower atmosphere for Mars, and there's, of course, to further understand what happens when we, say, bring a robot to Mars and understand that environment in terms of what happens between the exchange between the surface and the atmosphere. But you can also try to learn some of that skills and bring it to other planets. For example, Titan also has a really interesting atmosphere, and there's going to be Dragonfly is going to go there. So you can potentially also learn about the atmospheres in Titan, and then you can start developing these tool sets and doing what we call comparative climatology in the solar system. So you can start to try to understand how the different atmospheres on different terrestrial planets in the solar system compared to one another, and how the different systems differ. And there's something you can learn about the different planets that way.
You see, that's really cool because we know about Spinoff technology, where we get to learn about all these new inventions and gadgets that have come from space exploration. But it's very interesting to know that there is a climate model that we can develop for Earth by looking at other planetary bodies. And I don't think that's very well known, at least not outside the planetary science community.
So a lot of our climate models for the planetary sciences do have their origins from Earth climate models as well. For example, the type of regional scale atmospheric models that I've been using for Mars has its roots in weather prediction systems that are used on Earth. And so as we're learning more about how to have better forecast on Earth, we're also learning what we're developing for Earth models and applying those for Mars models and Titan models and Jupiter models and other models that are being used across the solar system.
Oh, so it's definitely a two-way system. It's not one planet benefits over the other.
Definitely not. There's a lot of cross benefits from understanding the different planetary systems.
Yeah, no, that's actually really cool. And I also noticed that you've had a little bit of experience from real planetary missions on top of the experience you got with the Phoenix mission as an undergrad. Do you want to touch a little bit more about all these other missions that you've been involved with?
I will say about the most recent one that I have some involvement in. It's because the Perseverance Rover is about to land on Mars on February 18th. And so we're only about 2.5 weeks at the time of the recording away from landing. And so because I do have some expertise in the Martian lower atmospheres, what we're doing as scientists is we're being involved in terms of helping evaluate the current Martian atmosphere to the entry, descent, and landing team for the Perseverance Rover, so that it could ensure a safe landing on landing day. And what we've been doing, this is called the Council of Atmospheres, is that so far we've been meeting every week. These frequencies will ramp up to twice a week, and then every day leading up to the day of landing. And what we're doing is evaluating the current atmospheric state. And so just like the Earth, Mars's atmosphere will change on a daily basis. There's a climatic mean in terms of what we think during this time of year, because Mars has seasons as well. We know that during landing, it will be in northern springtime on Mars. We know from the decades-long record of the Martian atmosphere from instruments like the TESS instrument or the MCS instrument, we have built up these decade-long baseline of what we think the atmosphere will do during this time of year. So we know what it's going to do. We have a good idea of what the baseline environment is, but there could be deviations and variations based on daily weather aspects of they're due to daily weather. And so we're currently monitoring using the instruments that are in space right now and looking at what the temperature profile is like, what the density profile is like, and also looking to see if there are regional dust storms that are going to come within the region of Jezero crater where Perseverance is going to land. And so by keeping our eyes out on what the weather on Mars is doing, we'll be able to adequately advise what the EDL team needs to know on landing day.
Yeah, because let's say when it comes to monitoring Mars weather, I know the big thing you already mentioned, the dust storms. It's regional, even globally, that these can occur, and they go by season, if I'm not mistaken. They're not random. You can get a general idea of when you're going to expect the next global dust storm. Am I right in saying this?
Yeah, there's definitely a high dust loading season on Mars, and that happens during perihelion. That's when the Earth and that's when Mars is closest to the sun in its orbit. And because Mars's orbit compared to the Earth is a little bit more elliptical, and so during its closest position to the sun, it actually happens during northern fall. So right now we're in northern springtime, which is right opposite of when dust storm season is. So luckily during this particular landing season, we're not expecting to have very high dust loading. So the global dust storms typically do not happen during this time of year. However, you can still have transient regional dust storms that can come through, and those appear much more sporadically.
Yeah, because I don't think we want another instant or an event that happened with the Opportunity rover where sadly it got caught in a giant dust storm, and I think that was the end game for the poor rover. It wasn't able to withstand the intense choking of dust on Mars.
Yeah, we were really lucky actually to have such long missions for both the MER rovers. Each of them were only expected to last 90 days, and we had much longer mission for both Spirit and Opportunity.
Yeah, I think Opportunity still baffles that. It's 90 days and it was 10 plus years still going. Yes, it mainly could just move, take pictures, and the instruments weren't really working that well, but it was still alive, and that was an engineering achievement on its own. So fingers crossed that maybe Mars Perseverance and I know the European ExoMars rover will get the same type of luck when it comes to a lifeline. They could just keep on going way past their expected mission time.
Yeah, for sure. And there's definitely an advantage of having a long baseline in the mission because we may be able to understand something from a 90-day mission. But when we have a 13-year mission, now you can see the repeatability of certain phenomena. And so you can see things that happen around the same time every year, and you can study how it changes from one year to the next. And so it definitely has that advantage of having a continuous baseline in your measurements.
No, that's actually a really good thing to think about. And it's good that everything's being considered, and the Mars Perseverance rover, it sounds like it's going to have a very clear landing. I don't want to say happy landing just yet. I'm just going to say clear landing.
Yes, we're all hoping for success.
And so with your work on these Mars missions, your background in outreach, I was just wondering, have you been able to talk about these missions and the reasons why they're happening to groups outside of the planetary science community? Oh, it's okay if you haven't. I was just curious.
I think space mission is definitely something that captures the attention and interest of the general public. And in addition, I think part of your podcast is to look at how space exploration really helps, is a benefit for everyone. So I think, yeah, space missions in particular is definitely something that is on the top of my interest, but also the different technology that space has enabled humanity is also something that I like to speak with when I engage with the public. And so I think I mentioned earlier that I did my bachelor's in Canada. And actually, historically, the Canadian Space Agency likes to focus on space-based technology that really improves telecommunication, navigation, and environmental monitoring. And those are primarily Earth-based. And so these space technology that enables us to go further into the solar system really originate first and foremost within our Earth system first. So we first sent satellites to orbit Earth before we were able to send them out to orbit Mars and to orbit Saturn and so on. And so during my undergrad training, I think the focus on telecommunication and environmental monitoring really instilled the importance that space technology has enhanced the lives of everyday people in our everyday lives. And so, yes, all of our high speed and broadband internet, and especially for Canada, given the sparse population that's spread out over a large amount of landmass. And so they were really a pioneer in terms of providing telecommunication to rural and remote parts of the country. And so I really try to let the public know that what we're learning about other planets, we also apply these to Earth as well. For NASA, there are different divisions, and planetary science is only one of 4 different divisions. Astrophysics is another one, solar physics is another one, and a large part of NASA funding actually goes towards Earth sciences. And what they do is to, part of those work is to understand environmental monitoring, like the changes in sea levels and changes in ice sheet coverage, or fire forecast and tornado forecast. And so those are the things that we watch our weather forecast and take that for granted, but a lot of decades of work has gone behind how we monitor tornadoes and extreme weather systems so that we could provide a safer environment for our everyday lives.
Yeah, you must get a lot of questions. I mean, you probably hit a common one all the time in that case, like, why do we invest all this money into a space mission that's going to visit a planet that I'm not ever going to visit? Why are we putting all of our money into this? And getting to talk, as you mentioned, getting to talk about all this Spinoff technology and how a large part of NASA is actually Earth sciences and Earth observation. It's something that's constantly monitoring us and helping us, making sure that we're staying safe, we're able to navigate, and we're able to communicate with pretty much lightning speed across the world, which is something that everyone always forgets when it comes to thinking about space. Because if it wasn't for space and satellites, we probably wouldn't be able to do a lot of the things that we do now.
Yeah, for sure. Definitely agree with you there.
Yeah, because that's probably one of the beautiful things about outreach. You get to bring this to the attention of people who are interested, and you can maybe, if people are always open to listening, you can enlighten people that maybe had no idea and maybe didn't show the same amount of interest. So I think it's something that everyone has to give a try in the planetary science community. Really don't try and sell the awesomeness of the space mission all the time. Just at least don't just sell just that. Because if they're not interested in how cool it is, you need to be able to tell them, but this is why we're doing it. Not just for the science, but this is what we're trying to get from it to bring back to Earth.
Right.
Yeah, I think something that a lot of us don't really think about sometimes. So Cecilia, I want to get to my favorite part of the podcast, which is the 3 questions that I ask all the guests. And well, the second one we've actually already touched on, but we'll get to that very soon. So the first question, if you could send a mission to any celestial body in the solar system, where would it go?
So for me, I think there's the really compelling case to go visit the ice giants again. We haven't visited them since the Voyager 2 mission, and that was a flyby more than 3 decades ago. And in particular, the Neptune Triton system is something I'm interested in. For Neptune, it receives only about 3% of the sunlight that Jupiter receives, yet the winds on Neptune is some of the strongest in the solar system. And also there's a lot of magnetic fields on Neptune that's highly tilted, and we haven't been able to figure that out quite yet. And so given that some of the other planets have been thoroughly explored at this time, and we do want to go back to those, we haven't been to Neptune or Uranus for a long time, and it's due for us to go back there. There is a really cool mission that is a finalist in the Discovery program called the Trident mission that will potentially go to Triton. And so Triton is the largest moon at Neptune. And so what makes Triton really interesting is that it has an icy landscape that's really young and has been resurfaced. And so we're trying to understand how that resurfacing might occur. And it also has really cool dark plumes of icy material that comes out of its surface. And so it's a target that's really interesting, and it's also potentially an ocean world. And so, yeah, I would really want to visit the Neptune Triton system if I can.
Does a part of you hope that there's cryovolcanism on that moon?
Oh, yes, that would be really cool.
Yeah, I think I remember when New Horizons arrived at Pluto, and then the whole hypothesis came up about volcanoes that could spew ice and water, which no one wanted to believe because everyone's thinking like, oh, how does that work? And it's like, well, just imagine a volcano, but instead of lava, it's just throwing out ice. So it's something to picture. And for the second question, we've already started talking about spin-off technology, but I wanted to ask you, what's your favorite spin-off technology?
Yeah, there have been so many wonderful examples. For me, the most interesting ones are medical imaging, such as MRIs and CAT scans. I think nowadays this technology is used to scan the internal structure of the body. It's widely used in medical applications. Yet it really is so interesting for me that this technology wasn't invented in a hospital or a lab, but it was because of digital signal processing techniques that were used to enhance images that came from the Apollo era. So it's just so cool that things that we use for moon missions have direct applications for life-saving technology on Earth. And how that came to be is because it's really expensive to send data across the solar system. And so, and also the resolution of it may not be as high as something that we take right here on Earth. And so back then, when we're sending data back from the moon, the way to it was a big part of it was to improve the image quality by increasing the signal to noise ratio. And so similar to the camera that we have on cell phones and little cameras, we can decrease the size of the camera, but you're also decreasing the size of your detector. And so something that's really important to do then is the technology behind increasing the signal so that you can get a better quality image. And so from the technology that is able to make out blurry images or low resolution images, we are applying what we know about that to medical imaging. And that, I think that's really cool in terms of a spin-off technology that really has important applications in terms of life-saving procedures.
No, that is a really good one. I actually didn't know that the idea of MRIs and CAT scans came from digital processing of Apollo images. I knew they were spin-off technologies, but I didn't realize where they came from and what mission. So I've learned something today, so I hope everyone else has as well. And for the final question, since this is the Diaries of Space Explorers, I wanted to ask you, who is your favorite space explorer?
Oh, there are so many of them, but I gave this a little bit of thought, and we all always hear about astronauts and explorers, but I think growing up as an Asian American, there weren't a lot of representations in terms of Asian American female astronauts that I could look up to. And so I think what really struck me was when Hidden Figures came out, and we're learning about all the roles that people that is not the typical names that you hear and associate with the Apollo mission, but the important roles that they play to enable a safe moon landing and missions. And it was really impactful for me to learn about these characters. And so for, I think the people that have started to really encourage and inspire me are some of my colleagues at JPL. And in one in particular is Mimi Ong. She's the project manager of the Mars helicopter. And so we talked a little bit about the Perseverance Rover, but there's also the Ingenuity helicopter that will be also being landed on the Red Planet in a couple of weeks. And so this is a technology demonstration flight experiment. And so this is the first time that any type of helicopter or rovercraft is going to take flight on Mars. And Mimi has this important role in terms of making sure the whole project comes together. For her, she describes this like when the Wright brothers was attempting flight for the first time. This is what she and her team are doing on Mars in just a few weeks. I think in terms of another JPLer that work should be highlighted, and we don't hear a lot of stories behind that, is Lin Pham. And she describes herself as the spacecraft dressmaker. And her role in JPL is she's a seamstress by training. She's actually the one that makes all of the protective thermal blankets on spacecraft. And so even though she didn't come from a technical science or engineering background, and she is a seamstress and an immigrant from Vietnam, she has this really important role to ensure that the spacecraft thermal requirements is just right. So the blankets actually provide just the right amount of heat, not too much and not too little, so that the spacecraft can operate correctly and properly. And so I think some of these stories and these women have really inspired me recently, because their stories are not as well known, but it makes it makes the space exploration and space sector a lot more relatable. And so that through them and through what their work and their role is in space exploration, I think it really shows that everybody has a role in the space exploration, and we're all invited in this joint human endeavor together.
No, I think everyone that you've mentioned are incredible inspirational space explorers to have. And it also shows that even if you didn't have maybe someone to look up to when you were younger, you were able to find your role models in the future, and they've still been able to help guide and inspire you to keep moving forward.
Yes, that's right. Yeah. And it's so important to have more of these stories represented in our history of space exploration.
Yeah, I completely agree. So Cecilia, I wanted to thank you for coming onto the podcast. It was great to learn about your journey, your thoughts on outreach and Mars sciences, and getting to learn about how we can learn about other planetary climates and our own climate by looking at other planets, which is something I didn't know, so I'm hoping everyone else can take that away today.
Thank you so much for inviting me to your podcast. I had a great time.
Oh, very good. Thank you. Thank you for listening to the Diaries of Space Explorers. We have been speaking with Dr. Cecilia Leung, a postdoctorate fellow at the Jet Propulsion Laboratory. If you would like to learn more about Cecilia's work and follow her to see her outreach events and activities, you can find her on Twitter at CelestialCess. I have been your host, Gavin Tolometti, and if you'd like to learn more about the show or recommend someone as a guest to come on the podcast, you can email us at thediariesofspaceexplorers@gmail.com. Or you can follow us on Twitter at Diaries of Space or on Instagram at Diaries of Space Explorers. We are always wanting to chat with space explorers on the podcast to help bridge the gap between the general public and the space sector around the world. Thank you for listening, and see you all next time.